Okay, now let's see if the design is verified. I was trying to do it before and I select analyze instead of verify. So you select and verify, and there we go. You have the design setting all set, 3D model all set, boundary and excitation is fine. The parameters is also good, and the analysis setup is there, and optometrics is there too. So you close that. Basically, optometrics is not there. We haven't defined anything that is wrong because we haven't defined anything. So now let me go ahead and select analyze all. It will take care of the analysis that we have. We have one type of analysis, which is magnetostatic. It's gonna be fast, and now it's finishing the mesh, and now it's calculating the forces, and it shouldn't take that long. I will come back when it's finished. Okay, now that the simulation is done, we can go ahead and check out a couple of things. First, you want to know how was the simulation, and to do that you can go into the Maxwell 3D design, Maxwell 3D, then results, results, and then you can go on solution data, and the solution data is here. That's one way of doing that. The other way is just go on the setup and right click on that, and then find the solution data. So when you click on that, you can get some information about what kind of a coverage you had. So right now I'm on force. Let me show you first. It was on force at the beginning, but I'm gonna go and show you the profile. So this is the profile of how much it takes, how many matrix we have, how much memory it used, and from that you can actually go ahead and like here we have 66 megabyte of memory, and we have also coverage. The plot, the type of the view right now here is in table by default. You can just make it plot, and you can see how it just converged, and sorry, type of converge, not the coverage. So the converge here is like after 5.5 paths. The number of tetrahedra units for the mesh increase a lot, so it will decrease the error. Most of the time it's the case. So that's how it gets the result. In the force section, you define the parameters. There we go, here it is. Note that the variations, we haven't defined any variation yet, but you can see that the C1 is in 100 milliamp, 100 amp, and MX is in 1 millimeters, the distance. So for these values, we have these parameters here. And now this is the force that we have in different fx, fy, and fz, and the magnitude of that. So we haven't defined matrix or torque or and mesh statistically soon for you. So then just consider it like this, and you press OK, close. Now to make sure that the B, the magnetic field is calculated correctly, we have to go ahead and see if we can see the magnetic field since the force is not enough. So to see it and visualize the magnetic B, go and select in the planes, go and set the global XY, and in the Maxwell 3D, go to results, sorry, to fields, again to fields, to B, and then to the B vector. Inside the B vector, you want to go ahead and see them be inside the core and as well as inside the magnet. So these are the B's that you want to see, the magnetic fields that you want to see. So you press and hold the control key in order to select both of them. Press done, and voila, you have your B. I'm gonna zoom in here and probably change it a bit so you can see what we have here. This is your B, makes pretty much a good sense. That's how it looks like. It's very neat here, and you have all your basically field inside the core, and it shows that the B is working well. Again, you should note that this is the nominal design, the nominal variables for C1 equals 100 amp and movement in the X directions of 1 millimeters. These are the values that we defined before, and we never changed it, so it's going to be for that. If we do change them separately, it will change the result. If you do it in the parametric manner, these values that we set at the beginning, where you can find it here by clicking on the Maxwell 3D design, and you can see it here 1 millimeters and 100 millimeters, these are going to be the one that is showing. Even if you change them in the optometrics, when you change them, it's not going to show it. These are the nominal values. These are the values you will see. But if you want to see that, you have to go ahead and make an optometric, and then in the optometric, when you got the results, you have to do some changes to see that. So let's do that, and let's see what is the difference, what is the basically effect of moving the object, and what is the effect of the current if I change the current as well. So now let's go ahead and start our first parametric analysis. Go ahead and select on optometrics and say add a parametric analysis. In that, you want to go ahead and in the sweep definitions, you want to go and say I want to add a new sweep. If it's MX, we don't care right now. We want to see what's the changes of the B when I change the current excitation inside the coil. But again, remember the coil, the core is BH curved. The permeability of that is non-linear. So if you change the input current, you will have a different result. And it's not going to be like if you increase the input current twice, you will have twice the magnetic fields. It's non-linear with different results, and that's the good things about the magnetostatic, because it will take care of that for you. In the eddy current, you can't do that. So you go here and sorry for that. You go here and select that. You say start value of 0 and the end value of 500 amps, crazy number, and you say the steps is going to be 100 amps each time. It's a linear step, so you will have a linear result. Add that, and you can see here what you have. If you want to see what are the variables that is going to change, the variable C1 is going to change from 0, 100, 200, 300, 400, and 500 amps. Okay, that's good. I'm satisfied with that. I go ahead and also in the options, I want to make sure that this option is also checked. Save fields and mesh. You want to make sure that you are saving the field and mesh for each different parameters. Okay, now you select OK on that, and you will start you will start running the design. So I'm gonna go to the optometrics, and I want to go ahead and right click on that and say analyze. So now I'm analyzing the entire thing. It should be fast because honestly the mesh is the same, so it's just like doing the passes. As you can see, because the BH curve, each time that the current changes, we have different set of adaptive passes. If it was not it was a linear permeability, it would be very faster than what you see here. You can see after the third one, you still have like sometimes calculating each time the B and H. It's not just multiplying the B or H. Okay, to save the time, I will come back when the simulation is finished. Okay, now the simulation is done, and we can now go ahead and check out what we have. First thing you want to do is you want to go ahead and right click on the parametric setup and check out the analysis result. And in here you can have take a look at the profile, and you can see how much time elapsed for each variation. And look at here, you have 21 second, 1 second for the next one. So 100 amp was not that much hard for it to realize, and then the curve actually get it more harder for it to realize. So 2 minutes, 2 minutes, 2 minutes, and then 2 minutes. So that's how it works actually. And these are the different variables and how much time it actually is spent for each variable. And so now you can realize how the result is looking. And now let's go ahead and plot the force for different current. To do that, you can do it in many different ways, but one way is to go to Maxwell 3D, and then you go and select the results, and then create magnetostatic report, and create a rectangular plot. And over here you can do that by right clicking here as well, but that's same thing. So you go on force, and you make sure that the parameters here is not none, it's actually force 1. If you remember, we defined force 1 in the parameters section, so we have the parameter force 1. We want to sweep it not with mx, with c1, because we haven't swept the mx, so we want to sweep it with c1. And then what kind of a force do we want to see? We want to see the force in the x directions, the force that is actually applied here in the x directions. So we go ahead and select x and a new report and close this one. Okay, in the x directions we have this negative force that is going, and as you can see, for larger values of the current, we have more force in the x direction. And I'm just double checking that I didn't miss anything. And okay, so everything is fine, and you can see it actually makes sense. When you increase the current, you have more force coming towards the bar that we have. Okay, last thing I want to do is to plot for you some cross-section of the B for different currents. And to do that, you can actually go ahead, in the tutorials it asks you to go and change the C1 here to whatever value that you want, and then you already have this plot from the previous step, and then look at the plot. That's one way to do that. I mean, if you go here and select this to 200 and press enter, you can see that it gets bigger. And if I say 500, you can see it's getting even bigger, and you can see it here. The other way you can see it is to actually go ahead and unfortunately you don't have this option in the Ansoft Maxwell. You have an options in HFSS that you can actually see how much is you can change the variable there. So one other thing you can do here instead is to go and animate it. So if you do animation from 0 to 10, and then it's gonna animate the C1 for all these different values, and hopefully you should be able to see the animations. You can see that, right? So that's how it increases and acts like this. Okay, you can export it, save it, or you do whatever you want. I'm gonna close it now and leave it like this. Okay, so far we learned how to find the B, how to calculate the force and see how much force we have. You learn also how to make a symmetric design and worked for a couple of very simple stages on the primitives and structures. And that's it for this tutorial. I'm gonna give you another tutorial on inductance calculations in let's say an three-phase inductor, and that is good if you want to calculate like efficiency and inductance in the transformers, three-phase transformers. And so that will be the next tutorial. Tune up and make sure that you like. If you have a comment, put it underneath each video. And thank you very much.